Okay, guys, my last video got cut off because someone came in, but let's pick it up with question 39. So, using equation 6.5, that should actually be 6.6, not 6.5, and it's on page 221 if you're trying to match it up with the book. Okay. So they want to know what the energy is at n equals 2 and n is equal to 6. We can use the same equation I used in the previous question with E is equal to negative 2.18 times 10 to the negative 18 joules. That is the Rydberg's constant, and it's not going anywhere. It's always going to be there. Times 1 over n squared. Look, that's supposed to be a superscript, not a subscript. Okay. So let's do the n is equal to 2 first. Negative 2.18 times 10 to the negative 18 times 1 over 2 squared. So that would be 1 over 4. When you do that calculation, your energy turns out to be negative, because of this negative here, 5.45 times 10 to the negative 19. Let's do n is equal to 6 now. I'm going to, instead of having that 2 there, I'm going to have that 6 there instead. 1 over, oops, sorry. Got a little ahead of myself. 2.18 negative times 10 to the negative 18 joules, 1 over 6 squared, which is 1 over 36. Which is then equal to 6.06 times 10 to the negative 20 joules. And again, that's going to be negative because the Rydberg constant's negative. Okay. The next question is asking us to use these two numbers and figure out the wavelength when it moves from 6 to 2. So in order to move from 6 to 2, is going to have the change of energy. So the 6 is going to be our initial, while the 2 is our final. So that means that this is our initial, and this is our final. So to find that delta E, we're going to subtract those two. Final minus the initial. Negative 5.45 times 10 to the negative 19 joules minus negative 6.06 times 10 to the negative 20th joules. Once we subtract that out, your final delta E is going to equal negative 4.84 times 10 to the negative 19 joules. From here, we are going to have to use the E is equal to H nu equation. We're trying to find the wavelength. You know that wavelength is C is equal to lambda nu. So in order to find lambda, which is the wavelength, we have to find the frequency first. So if this is our delta E, that's going to go into our energy equation. Remember, I called one energy equation, the other one the wavelength equation. So we're going to have to use the energy equation here. (6.626) times 10 to the negative 34 joule seconds times the frequency. So we're going to divide both sides by that. Now, because frequency is an absolute value, the negative goes away. And we end up with 7.31 times 10 to the 14th 1 over seconds for the frequency. Now that we have the frequency, now we can use the C is equal to lambda nu equation. And we're going to plug that in to the nu. C, again, is 3.0 times 10 to the 8th times the lambda times nu. To get lambda by itself, we're going to divide both sides by that 7.31. Lots of math in this one. Oh my goodness, oh my goodness. So that gives us a lambda. Remember, if you have times 10, that's the EE or EXP button on your calculator, is 4.1 times 10 to the negative 7th meters, which is also equivalent, in case they ask, a lot of times they do wavelengths as nanometers. 1 times 9 nanometers is equal to 1 meter. So I can convert this over to nanometers, and it would just be 410 nanometers. So 4.1 times 10 to the negative 7, or 410 nanometers. So what color is this 410? In order to do that, you'd have to match it up with the electromagnetic spectrum. So voila, we have one here. All right, so these are in nanometers. Notice that once again, they switch from times 10 to the something over to nanometers when they start talking about visible light. All right, so we had 410. Well, here's 380, here's 450. So it's going to be in this range here, which would be violet. All right, I'm going to stop it here, and we'll put 45 on the next slide because it's a fairly detailed question as well.